In this video, we'll be demonstrating how to do several topics in multiple linear regression in R. We're going to start out with polynomial regression using the CARS dataset. I'm going to go in and fit a model and then plot the data and add my regression line to the model. Now this is just a simple linear model with speed as the independent variable. Looking at this, I could do my hypothesis testing, make sure everything's in order. I'm just going to do a real quick check because this is going to be a pretty long video and I don't want it to take too much time here. Linearity looks okay. Looks like there might be some kind of slight curve here, which would justify us fitting a model, so maybe a quadratic term we could add. A couple potential outliers. Homogeneity variance looks fine, maybe a little smaller at the front end, a little bigger at the other, but data sparse enough that this could just be a natural pattern, and we just if we just had one or two data points over here, it would look fine. So everything looks fine here. Checking normality. Normality looks fine. Something at the end, but I think if we ran several normal graphs, this wouldn't be particularly uncommon. So everything looks relatively fine, and we could go on and interpret it. We see that the speed, as we would expect, is statistically significantly related to the distance that it takes to stop a car. But we did note that perhaps there could be a nonlinear relationship, a nonlinear model, but a nonlinear relationship that we can plot in a linear model. So we could try fitting a 2-degree polynomial. So I'm going to create the car speed squared, and then I'm going to fit something that I call quad mod, which has speed and speed squared. Now recall that there are some problems with multicollinearity if we do this without centering. So just to demonstrate, I've created speed and speed squared without centering the variable speed. Looking at my VIF, recall that we don't like to see values bigger than, it depends on who you ask, but maybe bigger than 5. In this case, we're seeing values at 24. So very, very high multicollinearity, very concerning. We wouldn't want to run or interpret this. And why wouldn't we want to do that? Well, consider what happens if we do interpret this. If we do interpret this, I see that neither of my variables are statistically significant. This would indicate that I shouldn't have either of these particular variables in the model. So speed is completely unrelated to the distance. Both the linear and the quadratic terms are unrelated to the distance that it takes to stop, and that would be an absolutely incorrect interpretation. And it purely stems from the fact that my multicollinearity is so high. So what could I do? Well, I could center speed. So I'm going to take speed minus the mean of speed. So that gives me the centered speed, and then I'm going to square that centered speed. So recall, when I center a variable, all of the higher dimensional polynomials that I add on should be using that centered variable. So the speed squared should be using the centered speed, and then I'm going to create a centered quadratic model. In the centered quadratic model, you can see that my variance inflation factor looks much, much, much better, very, very close to 1. And then when I interpret this, you can see quite clearly just a very large difference in our interpretation of what we would have had, and especially in terms of the linear component of the model. Now, it's important to state that actually in the highest order interaction or the highest order polynomial, that's not what changes when we center the model. What changes is the lower order terms, and in this case we see that both the intercept and the centered speed are statistically significant where they weren't earlier. Now, I mentioned in the lectures that we can use the poly command, so I would use poly. I'd give it the x, the independent variable, as the x argument, and then the degree of polynomial that I want. So I want a 2-degree polynomial, a quadratic term. And I can use the poly, and you'll note that the statistical significance is very close to what we had earlier. But note that the estimates, the parameter estimates, are very different because of the transformations that the poly command uses to make orthogonal components, the estimates for the particular parameters are not meaningful in a way in which we are discussing them. Actually, the way in which poly command makes orthogonal polynomials in some ways makes these more interpretable, but it does so in a way that we're not going to discuss in class. It does change the meaning from one to the other. So if I try to run VIF, that's not going to run. This doesn't run because we only have a single command in the model, so it doesn't have things to compare to. That's why it says contains fewer than 2 terms, but we can do it by hand. All we do is we make poly x a particular term and then, a little matrix there, and then we can run it. And what we see is if we run that, then the VIF is 1, as would be expected with orthogonal or completely independent terms. So part of the good part about using poly is that poly creates completely orthogonal independent variables, but we saw that even if we just hand-centered, it looked much, much, much better and made our parameter estimates much more interpretable. So what we can see is we can check. Now in our models, we saw that the linear term was statistically significant, but the quadratic term wasn't statistically significant. So we could consider removing the quadratic term. Note if this were the other way around, we could not consider removing the linear term because we need all lower order terms in the model if we want to keep the higher order term. So if the quadratic term was statistically significant, to keep it, we have to keep the linear term even if it's not statistically significant. But in this case, we could absolutely get rid of a higher order term if it were not statistically significant. We can check this using the ANOVA command, comparing our original model with the centered model that we came up with. And we can also test it the other way that it was done using the poly command. Note that both of these tests indicate that there is no statistically significant difference between the linear, the model with only the linear component and the model with the quadratic component. So using our little Occam's razor, preferring simpler models, then we would probably just go with the model with just the linear component. Also note that the statistical significance tests have the same p-value as the test of the quadratic parameter, and this is true when we only use the, recall this is kind of like a generalized f-test with a full and reduced model. So when we used a generalized f-test that only tests a single parameter at a time, then that is going to match up with our single parameter test in the regression model output. All right, so let's go down to categorical coding. So we'll use the MT cars and look at different cylinders effects on miles per gallon. So we have a variety of different cylinders. Cars come in 4, 6, and 8 cylinder versions in our data set. Now, one thing that I want to make sure that I do is to tell R that I'm going to be treating this cylinder as a categorical variable, or as R calls it, a factor. This is a really important step because if I don't do this, R is going to treat each of these numbers as numeric instead of categorical, and that can yield some problems if I'm trying to do it categorically. So this isn't always true, but whenever my variable is numbers, so 4, 6, 8, but in my mind, I'm treating it as different categories. A 4-cylinder, a 6-cylinder, or 8-cylinder are different categories of car. Then I need to make sure that I do use the as.factor command to redefine my data to be a factor in R, which again is what R uses to tell it that it's what we called a factor in our notes as well, a categorical variable. So I'm going to fit the model, MPG, squiggle cylinder, and then data equals dat, and I can check my assumptions really quickly here. Note that in our residual plot, this might freak you out a little bit. Don't stress too much about it with it being clumped up like this. This is just coming from the fact that I have 3 different groupings for my cylinders. Now, looking at this, it does look like this right-hand one has some higher variability than this middle one. I'm not going to worry about it for the class example, but this is something that you might investigate and look at using a transformation to fix. Normality looks fine. So it looks like only homogeneity variance would be something I'd worry about again. Were I focusing on that, then we would work on fixing that. But for the purposes of this class, I'm just going to move forward. So running summary mod, what you'll see is that R automatically breaks this down. Now it's important to realize that R does dummy coding by default. So recall I have cylinders 4, 6, and 8. We can see that R has created a cylinder 6 and a cylinder 8 dummy coded variable, which means that cylinder 4 is our reference group. So in cylinder 4, we see cylinder 4 gets 26 miles per gallon. Cylinder 6 gets 6.92 less miles per gallon than cylinder 4. So cylinder 6 doesn't get negative 6 miles per gallon. It gets 6.92 less miles per gallon than the reference group, which in this case is cylinder 4. Cylinder 8 gets 11.5 miles per gallon less than the reference group, which is cylinder 4. But note that there is no direct comparison between cylinder 6 and cylinder 8, and this is what we talked about in the notes as a limitation of categorical factors in the regression framework. All right, so the statistical significance tests test if these differences are greater than 0. That is cylinder 6 different than cylinder 4 in terms of the miles per gallon? And in this, there's evidence that cylinder 6 is statistically significantly different in the number of miles per gallon that six-cylinder cars get than cylinder 4. Same thing with 8-cylinder cars. All right. So I can, by hand, create dummy codes. So I'm going to create a cylinder 6 variable and a cylinder 8 variable by hand, just saying if the cylinder is 6, then it's going to be a 1, otherwise it's going to be 0. And then for the cylinder 8 dummy coded variable, if the cylinder is 8, it's going to be a 1, otherwise it's going to be a 0. And then I can add those to my data set and run the model here with these new variables and then look at the summary of running this by hand. Now I want to compare this to what R did by default just to demonstrate that up and above this is what I created by hand, down below this is what R did by default. These are the exact same, just to demonstrate that this is what R is doing behind the scenes if you just run it. Now the benefit of knowing how to run it your own way is that I could make a different group my reference group. In this case, R just uses 1 by default. You can change it. It's a bit of a workaround. You could absolutely change it. It's in the factor command. You can specify the reference group. All right, so all of this is dummy coding, but let's move on to effects coding. So for effects coding, I'm going to use the same structure of dummy coding, but now whenever it's the reference group, that'll be 4-cylinder. Recall that both of these coded variables are coded as -1 for the reference group, and this is the primary difference. Effects coding is dummy coding, literally copying over the dummy coded variables. The only difference is now whenever the factor is the reference group, the dummy coded variable is coded with a -1 instead of a 0, and that's what makes it an effects codes variable. So I'm going to go ahead, I have it here. You can check your data, make sure, okay, if it's 8-cylinder, it's marked as 1 in the 8-cylinder, 0 is the 6. If it's 6-cylinder, it's marked as 1 in the 6-cylinder, 0 in the 8. And then if it's 4-cylinder, it's marked as -1 on both. That looks like effects coding, so I'm good to go there. And then I can go ahead and fit the effects code model. Now note that this effects code model is going to be very different than what I had previously. Note that the parameter estimates are all different. So instead of the intercept being the 26 miles per gallon, which represented the 4-cylinder average of the miles per gallon, now the intercept is 20, which represents a weighted average of all of the different cylinders that I have. And it would be the overall average if I had equal sample sizes in each of the groups. Because this is the overall average, now I'm looking at the 6-cylinder as compared to the overall average. So 6-cylinder is less than 1 mile per gallon, or excuse me, less than 1 mile per gallon smaller than the overall average, and the 8 cylinders is about 5 miles per gallon smaller than the overall average. Now, because the interpretation of the coefficient and what the coefficient is discussing changes, our statistical significance testing also changes. So while the 6-cylinder was statistically significantly different than the 4-cylinder in terms of miles per gallon, the 6-cylinder is not statistically significantly different than the overall mean in terms of miles per gallon, though the 8-cylinder is statistically significantly different than the overall mean in terms of miles per gallon. Note how misunderstanding what the statistical significance terms are representing for the coded components of a single categorical variable can actually lead you to misinterpret and say, oh, 6-cylinder isn't important, but 8-cylinder is, when in fact it's just the way in which you phrase the test that could make this a very highly statistically significant component or a component that's not statistically significant at all. Looking at a box plot to indicate why this is going on, it actually kind of makes sense. Here's our 4-cylinder cars, here's our 6-cylinder cars, and here's our 8-cylinder cars. It makes sense that 6-cylinder and 4-cylinder are statistically significantly different from one another. But if you kind of consider, if I threw all of this data into a single pot and took an average, it would make sense why the 6-cylinder car is not statistically significantly different from that average, because the average is right around where that 6-cylinder or that middle category falls. So to test the overall effect of cylinder, we would use the reduced and the full model as we discussed in class. The reduced model with just the intercept is MPG squiggle 1. And then the full model is MPG squiggle the cylinder, which has both of the cylinder components in it. In this case, it would be dummy coded. And it doesn't particularly matter. Here's effects coded. You could just uncomment and run that, or just highlight and run that. It would give you the exact same variance explained by the model, so nothing would change if it's dummy coded or effect coded. From this test, I can see that the contribution of cylinder is statistically significant. Sometimes this happens when neither of the contributions of either of the coded components are statistically significant, but both of them taken together are statistically significant. That does happen. So in this particular case, it is the number of cylinders in a vehicle is statistically significantly related to the miles per gallon. So what would happen if we had another variable? How would we build the full and reduced model? So let's say I had the cylinders and I'm measuring the horsepower. Well, the full model has both of those, and then the reduced model just has horsepower left. And then I would compare again my full and reduced model and interpret the same way, that cylinder is contributes statistically significantly to the model. Now, we discussed how to do effects coding by hand. We can do it built in using the contrasts argument in the linear model. So we'd want some contrasts here. And if we look at the summary, now again, just like with the dummy coded, R by default uses its own components. So let me run our summary that we build by hand. So it creates its own comparison categories, and I guess it's not a comparison category or reference category with effects coding, it's the excluded category. So what we can see is that in this particular case, R has chosen to exclude the 8-cylinder group and include the 6-cylinder and the 4-cylinder group. The 4-cylinder is Sil 1, the 6-cylinder is Sil 2. Whereas in our hand model, we included the 6 and the 8-cylinder group. And again, it's one of the convenient features of knowing how to do this by hand. Now we can see that the estimates for the 6-cylinder group for the coefficient is the exact same, because we're comparing to the overall model. We're not comparing to the reference group. And so the overall average doesn't change if you use a different group that you exclude. Note also that the statistical significance of that doesn't change. So all this to say that these create the same model. The only thing that changes is our exclusion category, and you would have to putz around with R to do that. But by hand, I mean, you can exclude whatever category you want just by creating different variable sets. All right, so for the final component of this video, we'll talk about interaction models. I'll be using the tooth growth data set to demonstrate it. So we're going to look at the relationship between length and then dietary supplement and dosage. So we're going to quickly check our assumptions. So looking here, again, there might be some homogeneity variance. This one looks a little wider than that one. I'm not too worried about it. And normality looks just fine. So our assumptions look fine. Looking at the summary, first thing I want you to notice is that both dietary supplement and dose are factors, and actually I see here that dose isn't included as a factor, so I want to make sure that dose is a factor. So let me go on and add that $dose to be a factor. And then we'll rerun that model, make sure all of our plots still look good and they shouldn't change there. And then we run our summary command and we see dose 1 versus dose 2 and then our supplement VC and our interaction term. Note again, our interaction term involves all of the interactions between these. I should have mentioned earlier, I can't remember if I did or not, that to include an interaction, we use the star between two of our variables. To not include an interaction, we simply use plus. Now, if we wanted to write this out so that we included the interaction manually, star includes both the main effects and the interactions. But if we wanted to write this out so that we can include the interactions manually, we could use the colon, which indicates just the interaction. So this would be the main effect of supplement, the main effect of dose, and the interaction between the two. We could use the colon notation for that. But typically I'll just use the star between the variables that I care about. There's a couple other things you can do. You can use the caret key to indicate certain degrees of interactions that you want to study among, if you're looking at multiple independent variables and their interactions. But that's a bit beyond our scope. All right, so when we're looking at this, what we can see is that the interaction, one of the interaction terms is statistically significant. Now we could do a full-on check of this, but what it would turn out to be is that there is a statistically significant interaction, which means that we have to stop here and then look at our interaction plot to check out the nature of that interaction. So I'm going to use the interaction.plot command, which works if I'm dealing with categorical factors. I'll use the x factor as dose. The trace factor is how do you want to split up your different lines. So I'll split up my lines based on the supplement, and then the response is the length from the data. What I can see is that as dose increases, the length does increase, but that as dose goes from a single dose to a double dose, the effect of the VC supplement continues to be effective at increasing tooth length, but the OJ supplement kind of peters off and doesn't appear to be as effective when given a double dose. It is more effective than a single dose on average, it looks like, but it looks like it doesn't continue linearly upward. It looks like it might be leveling off there, but VC shows no sign of leveling off, at least in this graphic. Now, this is if the trace factor is categorical, but sometimes both of our variables are continuous. So if that's the case, I'm not going to use the interaction.plot from base R. What I'm going to actually use is interaction_plot from the interactions package. So I'm going to go on and build a quick model here. So let me see the... looks like my data isn't found here, so I'll go on and write states is state x77 is just a data set we'll use, and then we'll fit our model. So we're going to look at income as a function of illiteracy and murder rates in certain areas. All right, so I'm going to look at the model summary just like I would before. In the model summary, I see that we have a statistically significant interaction, and again, I stop here after seeing a statistically significant interaction, and then move to the interaction plot to guide interpretation. So what would happen if I didn't? Well, I'd say murder is statistically significantly related to income, and illiteracy is not statistically significantly related to income. So, and this would be a bad interpretation in regression anyway, but some would say, oh, well, illiteracy isn't important, but murder is. And that would be a bad interpretation of regression anyway, because remember, we're only looking at linear effects, and this isn't really on importance. This is on if we have enough data to support that the relationship is likely to be true in the population. So bad things going on here, but that's definitely how somebody could or would interpret this. But we, knowing that there's a statistically significant interaction, know that we need to look further. So let's look at the interaction plot. All right, so, I need my income model here. All right. So I've got my income model. So we're looking at this, and what I see is actually quite the opposite of illiteracy not being related at all to income. It looks like illiteracy can be highly related to income. That is, illiteracy goes up, income drastically goes down, especially for counties with high murder rates. But as illiteracy goes up for counties with low murder rates, it looks like income goes up, which is kind of strange, but there you go. So the impact of illiteracy on income is much, much larger than would otherwise have been interpreted had I just tried to interpret the main effects. So it's really important to make sure that I'm interpreting the effects of a model that has a statistically significant interaction using the interaction plot instead of using statistical tests for their main effects. All right, well, this has been a discussion of how to implement several of the main topics that we talked about for multiple linear regression, including polynomial models, incorporating categorical variables, and utilizing interactions with both categorical and continuous variables.